At low temperature, the Seebeck effect is mainly due to, remember that for high temperature, Seebeck effect is due to diffusion of electrons, and for low temperature, it is due to phonon drag. So at low temperature, the Seebeck effect is due to phonon drag of the electron, and at high temperatures, it is due to diffusion of the electrons. So option D is correct. This is assertion and reason question. Van der Waals type bonding single crystals do not exist at room temperature. This is false. Single crystals can exist at room temperature with van der Waals bonding. For example, graphite or noble gases like argon, they have weak van der Waals forces at room temperature. They do exist. So assertion is wrong. Van der Waals type single crystals are lightweight. This is also false. This lightweight has nothing to do with their stability or existence. Their weakness comes from weak intermolecular forces and not the mass. So assertion is also wrong and reason is also wrong. Both A and R are wrong. Magnetic susceptibility of a perfect diamagnet in CGS unit. Perfect diamagnet is nothing but superconductor in Meissner state. By definition, in CGS unit, by definition, we know that B is equals to H plus 4 pi m. For perfect diamagnet, the magnetic induction is 0. That is B is equals to 0. That means H plus 4 pi m is equals to 0. Magnetization M is equals to or 4 pi m is equals to minus H. M is equals to minus H by 4 pi. Now what they have asked? They have asked magnetic susceptibility. Susceptibility is nothing but magnetization by H, which is nothing but magnetization is minus H by 4 pi. 4 pi into H and H get cancelled, then susceptibility is minus 1 by 4 pi. Minus 1 by 4 pi. So option C is correct. Einstein's relation connecting the coefficient of diffusion with mobility is. The Einstein relation connecting the diffusion and mobility is given by D by nu is equals to kBT by E. This is the diffusion relation for Einstein diffusion coefficient and mobility, where D is the diffusion coefficient, mu is the mobility of the charge carriers, kBT is the Boltzmann constant absolute temperature, and E is the charge of the carrier. So we want diffusion coefficient, that is kBT into mu divided by E. So kBT nu into E. The paramagnetic susceptibility in the CGS unit is chi is equals to n nu square by kBT. N nu square by kBT. These are direct formulas. Heat capacity Cv of the metal is measured as the function of temperature T in the low temperature region. Assume that the measured Cv is due to both electrons and the lattice. Then the plot Cv by T versus T is. See, they have asked for low temperature. Specific heat at low temperatures has two contributions. One is from the electrons and one is from the lattice. Cv at low temperatures has two contributions, from the electrons and one is from the lattice. They have asked both for electrons and from the lattice. So from the electrons, the specific heat is given by gamma into T. This is from the Sommerfeld model. And from the lattice, the specific heat is given by beta into T cube. This is from D by T cube law. So the total heat capacity is Cv is equals to heat capacity from the electrons plus heat capacity from the lattice. That is Cv is equals to gamma into T plus beta by T cube. If we divide this equation by T, we get Cv by T is equals to gamma plus beta into T square. This Y is equals to mx plus C, where m is the slope, which is equals to beta, and C is the intercept, which is gamma. So from this equation we can see that if we plot a graph Cv by T versus T, we get a straight line. That is, it is linear in T square. So the plot Cv by T versus T is linear with the T square. So option B is correct. The electrical conductivity sigma is given by sigma is equals to Ne square tau by m, with the symbols having their conventional meaning. If E square by h is the unit of electrical conductivity, h being the Planck's constant, which of the following is dimensionless? So the electrical conductivity is given by sigma is equals to Ne square tau by m. In the question they have asked if the E square by h is the unit of electrical conductivity, then which of the expression in the option is dimensionless? So we want sigma by E square by h dimensionless. We want this value as dimensionless. Now substitute the value for sigma, Ne square tau by m into E square by h, which is Ne square tau by m into h by E square. E square and E square cancel, which is n tau h by m. So the dimensionless quantity is n tau h by m. So option B is correct. For a free electron gas in 2D, the variation of density of states as a function of energy is represented by, for free electron gas, the density of state versus energy, the density of states N versus energy E. For 1D, it is given by G of E is directly proportional to root E. For 2-dimensional, G of E is equals to constant, and for 3-dimensional, G of E is directly proportional to root E. So for 2-dimensional, G of E is constant. From the options, option C is correct, because the density of state versus energy for 2-dimensional is a constant. The variation of magnetic susceptibility as the function of temperature for a substance is shown below. The substance is more likely to. This is the typical behavior of an antiferromagnetic substance. As susceptibility increases, temperature first increases and then decreases. The susceptibility first increases. As susceptibility increases, temperature first increases and then decreases. This is the typical behavior for antiferromagnetic material. Diamagnetic material is, for diamagnetic material, susceptibility is independent of temperature. For paramagnetic materials, susceptibility follows Curie's law, that is 1 by T. That is, susceptibility is inversely proportional to 1 by T. For ferromagnetic material, it follows Curie-West law. Curie-West law, that is, susceptibility is equals to C by T minus Tc. So here, according to the graph, option C is correct. In BCS theory of superconductivity, the superconducting state formed from the pair of electrons act as, see, we know that in BCS theory, in the superconducting state, the pair of electrons formed are known as Cooper pairs. These Cooper pairs in the superconducting state act as bosons. We need to remember these. The value of flux on a superconductor in the SI unit is, in superconductor, the magnetic flux through the superconducting loop is quantized. The flux momentum is given by phi naught is equals to h by 2e, where h is Planck's constant and e is the charge of the electron. Planck's constant is given by 6.6 into 10 power minus 34 divided by 2 into charge of electron is 1.6 into 10 power minus 19 coulomb. So if we calculate it, 2 into 1.6 is 3.2. 6.6 divided by 3.2 is 2.06 into 10 power minus 34 plus 19 is 10 power minus 15. 10 power minus 15 Tesla meter square. 2.06 into 10 power minus 15 Tesla meter square. Option C is correct. The SI unit of flux is Tesla meter square or Weber. Weber is also the SI unit for a magnetic flux. The schematic arrangement shown in the figure is for measuring. See, we can see that here we are measuring temperature difference of two different metal A and B. This diagram is for Seebeck effect. Superfluidity in the state of matter in which the matter behaves like a fluid. The name itself says superfluidity. Superfluidity is a quantum phenomena observed in liquid helium and few other systems at very low temperature. Here that means the viscosity is effectively zero. So the superfluidity is a state of matter which behaves like a fluid with zero viscosity. According to Lorentz model, the Hall coefficient of the metals is given by, the Hall coefficient is given by RH is equals to EY JX into B, which is nothing but 1 by NE. So RH is equals to 1 by NE. According to Lorentz model, the Hall coefficient is given by 1 by NE. But here they have asked for metals. For metals, we know that electrons are the majority charge carriers. That means the net charge is negative. This net charge is negative. So RH is equals to minus 1 by E is correct for metals, because they have asked for metals. RH becomes positive when the majority charge carriers are holes. Here, since they have asked for metals, and we know that in metals the majority charge carriers are electrons, so the Hall coefficient is negative for metals. The frequency of the AC current produced when the DC voltage of 15 microvolt is applied across the Josephson junction. This question is solved by the formula for the frequency F is equals to 2 E into V divided by H, where E is the charge of the electron, H is the Planck's constant. Now if we calculate using this formula, we are not getting the satisfied answer. See, let us check. Frequency is equals to 2 into charge of electron is 1.6 into 10 power minus 19, and they have given voltage that is 15 microvolt, that is 10 power minus 6, divided by Planck's constant is 6.63 into 10 power minus 34. Now if we calculate this, 2 into 1.6 into 15 is 48 into 10 power minus 19 minus 6 is minus 25 divided by 6.63 into 10 power minus 34, which is nothing but 48 divided by 6.63 is 7.23 into 10 power minus 25 plus 34, 10 power 9. So the answer is coming up to 7.23 gigahertz. 10 power 9 is nothing but gigahertz. But here in the options 7.23 is not there. Also, I'm not sure about this question. For 2013 paper 3, I'm not finding any answer keys. Maybe this was the Grace question. The options are not correct. If we calculate this, we will get 7.23 gigahertz. Now the answer is in gigahertz. Mostly the option might be B, or they have given grace marks. I don't know. It is 2013 paper. So whenever this type of question is asked, use this formula for calculation. If E is the electric field developed in the presence of a temperature gradient maintained at the ends of the metal rod under open circuit condition, then the constant of the proportionality in the equation is. So they have asked this proportionality constant. What is this proportionality constant in this equation? Let us understand what this actually means. See, whenever we heat If this is a metal rod, if we heat one end of the metal rod and keep the other end cool, the electrons from the hot end gain more energy. These high energy electrons starts to move towards the cooler end. This motion of the charge creates a potential difference across the end of the rod. So if we heat one end of the metal, the electrons at the hot end gain high energy. These high energy electrons move from hot end to cold end. This motion of the charge creates the potential difference across the rod. Now, since it is under open circuit condition, meaning no current is allowed to flow, what happens is an electric field is developed inside the rod. When it is under open circuit condition, an electric field is developed inside the rod to balance the motion of the charges. This is basically the foundation of the Seebeck effect. The Seebeck effect we can mathematically write as E is equals to L dot gradient S dot gradient of T, where S is known as Seebeck coefficient. Seebeck coefficient. So here in the question, instead of S, they have written C. E is equals to C dot gradient of T, where C is the Seebeck coefficient under open circuit condition. If E is the electric field developed in the presence of the temperature gradient maintained at the ends of the metal rod under open circuit condition, then the constant proportionality in the equation is the Seebeck coefficient. Match the following. Here they have given the terms and we have to match their SI units. Match the following. Here they have given some physical terms and we have to match their SI units. Specific heat is the heat required to raise the temperature of 1 mole of substance by 1 Kelvin. Specific heat is the heat required to raise the temperature of 1 mole of substance by 1 Kelvin. So its SI unit is Joule per mole per Kelvin. SI unit of specific heat is Joule per mole per Kelvin. Carrier mobility. Carrier mobility tells us how fast an electron and hole can move in the material under an applied electric field. If we apply an electric field, how fast the electrons and holes can move in that material is known as carrier mobility. The carrier mobility is given by mu is equals to drift velocity by electric field. The unit is meter square per volt per second. Carrier mobility meter square per volt per second. Thermal conductivity. This thermal conductivity describes how easily the material conducts heat. Its SI unit is watt per meter per Kelvin. Thermoelectric power. Thermoelectric power is also called as Seebeck coefficient. This what we have seen in the previous question. This Seebeck coefficient, it is also known as thermoelectric power. So here from this equation we can see that E is equals to L dot gradient of T and S is equals to E divided by del T, which is nothing but V volt per Kelvin. So the SI unit for thermoelectric power or Seebeck coefficient is volt per Kelvin. So specific heat is B, 1 is B. So these options are not correct. Mobility, carrier mobility is D, 2D. So this option is also wrong. So thermal conductivity 3A and 4C. So option C is correct. I will give the formulas for each of these physical terms. Specific heat's formula is given by C is equals to Q divided by N into del T. This is the formula for specific heat. For mobility, mu is equals to drift velocity by electric field. And thermal conductivity is given by Q is equals to minus K dt by dx. and this thermoelectric power S is equals to E divided by gradient of T. Type 2 superconductors are characterized by two critical magnetic field Hc1 and Hc2. These materials are used for making very high field electromagnets. These materials show, see, we know that superconductors are the conductors where below a certain critical temperature the resistance drops to zero. If a substance resistance is zero, it is known as superconductors. When we apply a magnetic field to this superconductors expels the magnetic field completely. This effect is known as Meissner's effect. Now there are two types of superconductors, type 1 superconductors and type 2 superconductors. In type 1 superconductor, only one critical field is present, that is Hc. When a magnetic field is applied, they completely expel the magnetic field only at Hc, then suddenly becomes normal. In type 2 superconductors, we have two critical field, Hc1 and Hc2. Below Hc1, the superconductor shows perfect Meissner's effect. That means the superconductor expels the magnetic field completely. Between Hc1 and Hc2, the magnetic field partially penetrates. It is called the mixed state. Above Hc2, the material becomes normal. The superconductor becomes normal. Below Hc1, perfect Meissner effect or superconducting state. Between Hc1 and Hc2, mixed state. It is also known as vortices state. Above Hc2, the superconductor becomes normal. This property of the type 2 superconductors are useful for very high magnetic fields like electromagnets in MRI machines and practical accelerators. So in the question, they have asked about type 2 superconductors. Type 2 superconductors are characterized by two critical fields, two critical magnetic fields, Hc1 and Hc2. These materials are used for making very high field electromagnets. These materials show Meissner's effect up to Hc1. Yes, they show Meissner's effect up to Hc1 and constant magnetization between Hc1 and Hc2. This constant magnetization is also called mixed state. So option A is correct. Meissner's effect up to Hc1. They show Meissner's effect up to Hc1 and constant magnetization between Hc1 and Hc2. Match the following with their resistivity values at room temperature. Resistivity depends on how freely charge moves. So in metals, the resistivity is very low. In insulators, the resistivity is very high. For metals, resistivity is very low, and for insulators, the resistivity is very high. So for copper, see, copper is a metal. So metals has very low resistivity. Find the option here that has very less resistivity. 10 power minus 8, 1.68 into 10 power minus 8 has very low resistivity. So copper has the least resistivity value. This fused quartz is a strong insulator. That means insulators have very high resistivity. Find the options that has the highest resistivity. 10 power 17. So quartz has the highest resistivity of 7.5 into 10 power 17. Seawater is salty water. It has ions. Since it has ions, so its resistivity is lower compared to pure water. So find the resistivity that is again less compared to the metals such as copper. So the next lowest resistivity is 10 power minus 1. So seawater has the resistivity of 2 into 10 power minus 1 ohm meter. So deionized water is a very pure water. This pure water has very high resistivity compared to seawater, but not much higher resistivity compared to the insulators such as fused quartz. So deionized water has highest resistivity but not higher than the insulators. So this 10 power 5. So deionized water has the resistivity of 1.8 into 10 power 5 ohm meter. So 1A, 2D, 3B and 4C. Option B is correct. The total specific heat of a metal at low temperature is plotted as the function of temperature, which is shown in the figure. The electronic specific heat is C. Specific heat at low temperatures has two contributions. One is electronic contribution and another is lattice vibration. From electronic contribution, the specific heat is given by Cv is equals to gamma into T. And from the lattice contribution, the specific heat Cv is given by beta into T cube. So the total specific heat is Cv is equals to gamma into T plus beta into T cube, where gamma is the electronic specific heat. Gamma is the electronic specific heat and beta is the lattice specific heat. Gamma is the electronic specific heat because it comes from the electronic contribution. Beta is the lattice specific heat because it comes from the lattice contribution. So here they have plotted a graph Cv by T versus T square. So if we divide this equation by T, Cv is equals to Cv by T gamma plus beta into T square. This equation follows the equation of straight line y is equals to mx plus c, where m is the slope which is beta, m is the slope which is beta, c is the intercept which is given by gamma. So the lattice specific heat is given by the slope of this graph and gamma is the electronic specific heat which is given by the intercept of this graph. So in question they have asked the electronic specific heat. So they have asked about gamma. So the electronic specific heat in this graph is obtained from the y-intercept. So option B is correct. Josephson effect provides a standard for. So let us see what is Josephson effect first. When two superconductors, this is a superconductor, this is a superconductor. When two superconductors are separated by a thin insulating film, this is an insulator. When two superconductors are separated by a thin insulating barrier, this setup is known as Josephson junction. Even though there is an insulator in between the two superconductors, the Cooper pairs can travel through the barrier. What are Cooper pairs? Cooper pairs are the pair of electrons in the superconductors. Even though there is an insulating barrier in between two superconductors, the Cooper pairs can tunnel through this insulating barrier. This tunneling is known as Josephson tunneling. Josephson tunneling. This tunneling leads to two types of effect. One is DC Josephson effect and another one is AC Josephson effect. In DC Josephson effect, a constant current flows without any applied voltage. A constant current flows without any applied voltage. In AC Josephson effect, if we apply a DC voltage, the current oscillates with the frequency directly proportional to that of the voltage. In AC Josephson effect, if we apply a DC voltage, the current will have the frequency which is directly proportional to the voltage. The frequency of this oscillation is given by F is equals to 2E by H into V, where E is the charge of the electron, H is the Planck's constant and V is the voltage across the junction. This means that if we measure the frequency, we can determine the voltage. So the Josephson effect provides the standard for the voltage. So Josephson junction, what is Josephson junction? When two superconductors are separated by the thin insulating barrier, this is known as Josephson junction. The Cooper pairs can tunnel through the superconductors even though there is an insulating barrier in between. This tunneling is known as Josephson effect. There are two types of Josephson effect, DC Josephson effect and AC Josephson effect. In DC Josephson effect, a current is produced even when there is no applied voltage. In AC Josephson effect, the frequency is directly proportional to the voltage. That is why it is used as the voltage standard. So the Josephson effect provides a standard for voltage. So option B is correct. It is difficult to determine the Hall coefficient for a metal as compared to semiconductor, because see, we know that the Hall coefficient is given by RH is equals to EY divided by Jx into Bz, which is equals to 1 by n into E. So Hall coefficient is equals to 1 by n into E, where n is the carrier concentration and E is the charge. So Hall effect basically depends upon how many free charge carriers are present. So in metals, the charge carriers are very high n. So in metals, the number of charge carriers are very high, and in superconductors the charge carriers are very low. So in semiconductors, the charge carriers are very low. So for metals, the Hall coefficient is very low because the charge carriers are very high in metals. If charge carriers are high, Hall coefficient will decrease. So for metals and for semiconductors, the Hall coefficient is very high because the number of free charge carriers is less. So it is difficult to determine the Hall coefficient for a metal as compared to the semiconductor, because Hall coefficient will be too small. Yes, if the metals, in the metals, the charge carriers are very high, that means the Hall coefficient will be very low. The density of states in the conduction band for electrons assumed to be essentially free in 2 dimension. They have asked for 2D is proportional to. See, density of states for 1D is directly proportional to 1 by root E. And density of states for 2D is independent of E. That means it is directly proportional to e to the power of 0, and in 3D the density of states is directly proportional to root E. So for 2 dimension, density of states is independent of E. So they have asked for 2 dimension, so the density of states in 2 dimension is e to the power of 0. In the longer wavelength regime, the dispersion relation for magnons in the ferromagnet in 1 dimension with the nearest neighbor interaction yields. According to Heisenberg model, the spin wave dispersion relation is given by omega k. Omega k is equals to Js into Ka whole square. That means omega k is equals to Js k square into a square, or omega k is directly proportional to k square. So omega k is directly proportional to k square. The polarization P in the solid dielectric is related to the electric field E and electric flux density D by the relation. So the polarization is related to electric field and flux density D by D is equals to epsilon naught E plus P. Paramagnetic susceptibility of Fermi gas of conduction electron is, the paramagnetic susceptibility for conduction electron follows Curie's law, that is, susceptibility is inversely proportional to T. This is for classical paramagnetic materials. Classical paramagnetic materials, susceptibility is inversely proportional to temperature, but they have asked for conduction electron. Fermi gas of conduction electron. For Fermi gas, susceptibility is independent of temperature. Paramagnetic susceptibility is independent of temperature. This is for Fermi gas. Fermi gas, paramagnetic susceptibility is independent of temperature. For the classical paramagnetic materials follows Curie's law, that is, susceptibility is inversely proportional to temperature. So the paramagnetic susceptibility of Fermi gas of the conduction electron is independent of the temperature. The heat capacity of superconducting state is proportional to, the heat capacity in superconducting state, See, in normal state the specific heat is directly proportional to kBT. In normal state. In superconducting state, the specific heat is directly proportional to e to the power of minus del by kBT. So in superconducting state, specific heat is directly proportional to minus del divided by kBT, and in normal state, specific heat is directly proportional to kBT. So if I have asked for superconducting state, it is directly proportional to minus del by kBT. Madelung constant for one dimensional crystal of the infinite line of ions of alternate signs. See, in one dimension, Madelung constant, that is alpha, Madelung constant is alpha, in one dimension of alternate signs. For alternating signs, it is always 2 ln 2 for alternating signs, and for same signs like plus, 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 and for same signs, it is finite. Infinite for alternate signs, finite for same signs. So option D is correct. 4 ln 2 is for 2D square lattice. 2D square lattice. 3 ln 2 is for 2D triangular lattice. 2D triangular lattice. The low temperature heat capacity of insulators will be proportional to, see, I talked about heat capacity at low temperatures in the previous questions. The heat capacity at low temperatures has two contribution. One is electronic contribution and one is lattice contribution, lattice vibration contribution. They have asked for insulators. In insulators, the electronic contribution is negligible because there are no free electrons. So electronic contribution in insulators are negligible. The heat capacity comes from the lattice vibrations, that is from the phonons. So I told that the lattice contribution is given by, the specific heat from the lattice contribution is given by beta into T cube, that comes from the D by T cube law. So specific heat is directly proportional to T cube from the lattice contribution of the insulators. So it is directly proportional to T cube. The Wigner-Seitz cell for any two-dimensional Bravais lattice is hexagonal or rectangle for two-dimension Bravais lattice. The Love condition for X-ray diffraction is, the Love condition for X-ray diffraction is given by kg is equals to g square by 2, or 2 kg is equals to g square. This comes from a derivation, so just remember this. So option A is correct. 2 kg is equals to g square. The dielectric function at frequency omega for a free electron gas is equals to, so the dielectric function at frequency omega for the free electron gas is equals to 1 minus 4 pi Ne square by m omega square. Iron possesses the following magnetism. See, iron is a classic ferromagnetic material. That means it exhibits ferromagnetism, but not pure. See, the materials are not always 100% pure. In one sense, if we consider, even in ferromagnetic materials like iron, diamagnetism is also present. But it's extremely weak and usually negligible compared to ferromagnetism. But every material shows some diamagnetism because of the orbital motion of the electrons slightly opposes the magnetic field. So, if strictly speaking, iron shows ferromagnetism and also has a slightly or tiny contribution of the diamagnetism. So, iron possesses ferromagnetism and diamagnetism, not pure magnetism, because pure would mean ignoring the tiny diamagnetic effect. Ferrimagnetism and paramagnetism doesn't apply to iron. So, I have completed all the previous year questions for the CMP. You will get this PDF in the Telegram channel. I have linked the Telegram channel in the description. Next, I will start with the NPP questions. Thank you.